Hello guys. You're welcome to another lesson plan B on that reduction formula. Um, from the first video, from lesson plan A, we were able to generate the reduction formula for integral of sine nx dx. So similarly, it's time for us to generate the reduction formula for cos nx dx using the same process we have actually used in lesson plan A. So considering this second part, we actually want to integrate cos of nx dx using the same expression. If you remember, the first thing I said was let in represent the question given to you, which is cos nx dx, and at the same time then I actually asked you to manipulate by using this expression. I said that this cos nx can also be written as cos n minus 1 of x times cos x, then with this dx. You know, when you multiply this and this together, you still end up having cos nx back. This is very easy. I said this is cos n minus 1 of x, which can still be written as cos n minus 1, cos x of n minus 1, then times cos x. So this is very direct. Using the rule of indices, you should have cos x. If you have the same base but with different powers or maybe the same powers, you should have cos x is common and then you sum up the powers together. So leaving you with just ordinary n, which is cos x raised to the power of n. And this is still the same thing. So having this expression indicates that we have not tampered what is given to us as the question. So it's still the same thing. Then when you decide to move a step forward from here, that is the next step. We decide to use integration by parts, like I said in the first video. So using integration by parts, using integration by part as IBP, the first thing you need to consider is that you need to let u represent whatever you have here, which is cos n minus 1 of x, and at the same time let the v represent cos x, the whole of that dx, such that the question I want to solve, this in, which is equals to integral of cos n minus 1 x cos x dx. Since I'm already using integration by parts, this expression becomes uv minus integral of v du. So here in this case, I know what u is. U is cos n minus 1 of x, but I don't know what v is. So from here, I can decide to get what v is all about. So from dv equals to cos x dx, if we decide to integrate both sides, then we can easily generate what our v is. If you integrate the v, you have v. You know, when you integrate a constant with respect to any variable you want, you have that variable back. That is, integrate dv simply implies integrate 1 times dv, right? And at the same time, it is integrate, this 1 can still be written as v raised to the power of 0 then dv. And at the same time, if I integrate something like this, like integrate x dx, so you know what to do. So from here, I can just say, okay, if I integrate v raised to the power of 0 dv, that should be v raised to the power of 0 plus 1 over the power 0 plus 1. Then that gives us what? V raised to the power of 1 over 1, and that's v over 1, and that's v. So that is the reason why integral of the v is v. So I've been able to show it here, right? So we don't have any problem with that. So integrate cos x. When you integrate cos x, the result is sin x. That's standard integral. So I can decide to substitute. So when you continue with this, I will have in equals to uv, right? This is u, and my u is what? Cos of n minus 1 of x, right? Times v is sin x, very good, and at the same time followed by a negative sign. Then I need to integrate v du. V is sin x, du, we have not differentiated u, okay? So I need du. From here we have u equals to cos n minus 1 of x. So if I need du, that is du over dx, I can differentiate this u with respect to x. So I'm using the same pattern for this, such that this power needs to be the coefficient first. It comes down, leaving us with n minus 1. Multiply it by differentiate cos x, and that will give us minus sin x. And at the same time, you need to multiply it by repeating everything you have for your u. Repeat everything back, but you need to subtract 1. So I think you should have done this in Mat251 calculus last semester. So then from here, whatever we have left should be du over dx equals a negative sign of n minus 1 of sine x, right, multiplied by cos minus 1, that's n minus 2 of x. So when you multiply both sides by dx, then you should end up having, when you multiply by dx, this will cancel this. Then du will give us minus of n minus 1 of sine x, then cos n minus 2 of x dx. So this is what I have for du. So I'll just come here and substitute. Du is whatever I have here. V du, this is v, then du is all this expression. So it is negative of n minus 1 sine x, then cos n minus 2 of x dx. So to go further, so we can proceed by saying, okay, this negative sign, multiply this negative sign, such that we end up having minus times minus gives us plus. This constant come outside from the bracket, from the integral sign, n minus 1 come outside, and then we end up having, what do you have left? Sine x, that gives us sine square x, right? And at the same time, we have cos n minus 2 of x dx left. So it's making sense. The next thing for us to do from here is that I remember when I did the previous video from the lesson, or from the tutorial, I believe that I said sine square x. We believe that sine square x plus cos square x is equals to 1. So if you make sine square x the source of the formula, we end up having 1 minus cos square x. So that should be cos n minus 1 of x sine x plus n minus 1. Then this sine square x, we end up having 1 minus cos square x. So that's not a problem. Then you multiply it by cos n minus 2 of x dx. So the next thing to do from here is to open up this bracket. So when I open it up, I will end up having this still repeated, then plus n minus 1, right? And the next thing to do here is that I also do it straight up. Okay, let me just take it one by one. This is integral, so I want to expand this bracket, leaving us with 1 times the whole of this. That gives me what? Cos n minus 2 of x dx, right? Then minus cos square x times the whole of this. I will end up having minus, minus times plus is minus, then this multiply this, 2 will cancel 2. When you add up the powers, 2 plus n minus 2, then I will end up having just n left, cos n of x then dx. So then the next thing to do from here also is to split up the integrals. Open this bracket, the whole of this bracket, with this n minus 1. So we are going to be having in equals cos n minus 1 of x sine x. If this n minus 1 multiply this expression here, I will end up having n minus 1 integral n minus 1 integral of cos n minus 2 of x dx. And at the same time, plus times minus gives us minus. N minus 1 integral times the whole of this gives us n minus 1 integral of what? Cos nx dx. So we actually make an assumption from the beginning. We let in to represent cos n minus. We let in represent cos nx, as you can see. So similarly, if I have n minus 1 or n minus 2, then whatever I have here is actually based on whatever you have in the question as the power for the trig function. So here I have n, I should have n. So if I have n minus 2, so that means I'm supposed to have, okay, we actually stop here. Then the next thing here is that when I have cos n minus 2 of x dx, integral of cos n minus 2 of x dx, it is actually equivalent to in minus 2. I hope you agree with that. So that will be cos of n minus 1 of x, then sine x plus n minus 1. Then the whole of this becomes I of n minus 2. I hope you agree with that. So minus n minus 1. The whole of this is cos nx, and that's our first assumption from the question. So then I end up having in here, this in. So trivially, it is clearly seen that in is here, and in is also on the right hand side. So I'll collect like terms. So I'll take this to the other side. In, when you add n minus 1 of in to both sides, you end up having plus n minus 1 of in equals, then this, you have n minus 1, in minus 2. Anyhow you want it, you can rearrange it or you leave it like this. It does not affect the solution or the final answer for the question. So from here, it is then equal to in. Then we have in is common in the, from this left hand side. So in cancel in, I have 1 plus. Cancel this, I have n minus 1 left, right? Then leaving us with n minus 1 of in minus 2 plus cos of n minus 1 of x sine x. So 1 cancel minus 1. All I have left here is just n. So when this n multiply this in, I have n equals n minus 1 of in minus 2 plus cos of n minus 1 of x sine x. Multiply both sides by 1 over n so that you end up cancelling this 1 over n. The whole of this multiplied by 1 over n. You have to be very careful, you know, there's a positive sign here. You have two terms that is being separated by either plus or minus. So you have to put in a full bracket and then multiply by 1 over n. This cancels this. Hence, the final answer is in equals n. We end up having okay, let's just write it very well. We have 1 over n here multiplying the whole of this. So that should be 1 over n multiplied by n minus 1 of in minus 2 plus sine x cos n minus 1 of x. So this result here gives us the final answer. Remember that in is, we actually made an assumption that in represents cos nx dx, and this is what you're actually looking for. So this gives us the what, the reduction formula for cos nx dx. So to make a generalization, just to recall whatever we have done so far. So this gives the final answer for cos nx, which is very, very straightforward. So let me just remind you of this. So to make a summary on for lesson plan A and B, remember that from the first video, we tried to generate the formula for the reduction formula for sine nx dx, right? So this actually gives us this final answer. We end up having 1 over n. You can cram it. It's better you just know it, okay? Because you don't have to prove all these things before you could simplify sine raised to power of 7 over x. You have to know the formula. So you must create a pattern for yourself. So here in this case, you have sine nx dx to be equals to 1 over n. Then you open a full bracket. So always remember that whatever you have here, whatever you should have here should be based on n minus 1. This one is fixed, of in minus 2. So the difference between integral of sine, I want to show you something so that you can easily grab it once and for all. So it's not difficult to cram. You have 1 over n, this thing here and this thing here are always fixed for both reduction formula for sine x and cosine x. They are both fixed. Nothing is wrong with them. So the difference between the two of them is that in this case you should have minus, and in this case you are expected to have what? You are expected to have what? Plus. Yes. You can try to confirm that. So for sine nx dx, whatever you should have here is cos x is multiplying something, but here it is sine x that's multiplying the other part. So here in this case, cos x is multiplying it's actually multiplying sine, whatever you have here, sine of n minus 1 of x, and that ends the formula. But here in this case, the sine x you have here, similarly, when I want to multiply it, I said consider this sign and put minus 1 here. In this case too, multiply it by whatever you have here from the question, cos n minus 1 of x. You see, so it is very easier to cram. It's very easy to cram. So for the next video, I'm going to show you how to get the reduction formula for what? Tan nx, and then followed by cot nx, then sec and cosec. So please subscribe to my YouTube channel and click on like button, and also remember to meet me in the next video.